Welcome back to our heat transfer class, where we are delving deeper into the fascinating world of thermal energy exchange. This video was made with the support of InnoEnergy. Remember that the introduction to heat transfer is divided into several lessons. In this 9th and final lesson, we are about to discover the secrets of analyzing heat transfer problems. Let's answer the burning question. After having studied the law of conservation of energy and rate equations, how can you develop a mathematical model to calculate temperatures and heat transfer rates? Let's go step by step.
Consider a large wall, whose thickness is L, its thermal conductivity is lambda, and its internal heat generation, G, is uniform. At a certain time t, the temperature distribution through the wall is a second-order polynomial. For a wall surface of 1 square meter, what is the value of the stored energy per unit time in watts at a given instant of time? When the values of A, B and C are those in the table? Start by defining the control volume and applying the energy conservation equation. And identify the energy terms. Energy inputs, energy outputs, energy generation, and energy storage. The generation term is the result of multiplying the volumetric heat generation by the volume of the control volume, which is a times L. Inputs and outputs can be calculated by applying Fourier's law in the surface of the control volume. For x equal to 0, the wall is insulated and the heat flux is 0. At x equal to L, the heat transfer rate is 1,530 watts. The final result is 3,120 watts.
Conduction inside a solid.
Let's focus in a laterally insulated cylinder. In the steady state, without internal generation, and using the data in the table, calculate the heat transfer rate between the two extremes. For solving this exercise, you can apply the Laplace equation for temperature, which is an ordinary second-order differential equation. By integrating once, you can see that the derivative is constant. Therefore, the first consequence for this type of system is that the temperature distribution is a straight line. Now, for a second-order differential equation, you have to define two boundary conditions. In this particular case, you know the temperature at x equals 0 and the temperature at x equals L. From the boundary condition at x equals 0, we deduce that C2 equals T1. From the boundary condition at x equals L, we can find the expression of C1 as a function of the temperatures and the length of the cylinder. Combining all these results, we obtain T as a function of x. Once you have the expression for the temperature profile, you can find the derivative and apply Fourier's law. Therefore, the heat flow is equal to the thermal conductivity times the temperature difference divided by the length of the cylinder. Substituting the values of the statement in the expression of the heat flux, you can find the result. The heat flux is very high. However, the heat transfer rate is small because the cross-sectional area is small.
Heat losses in the surface of a solid.
A square section chip with a side of W equals 100 mm is insulated on all its faces except for the upper face. This face is exposed to a coolant at T infinity with a convection coefficient H. The chip top surface temperature must not exceed 65 Celsius degrees. What is the maximum allowable electrical power the chip can consume? Analyze the 6 cases using the data for the coolant temperature and convection coefficient shown in the table. Stop the video now and try to calculate the maximum power for each case. Additionally, analyze the results. Have you solved this exercise on your own? What conclusions have you drawn from the results? But let's first look at the methodology for calculating these results. Start defining as control volume the volume of the chip and applying the conservation equation. As the chip is in steady state, there is no stored energy. As the chip is perfectly insulated at the bottom, there will only be one convection output on the surface and no input. Therefore, in the steady state, the electrical power consumed by the chip equals the heat transfer rate at its surface. Now, you can apply Newton's law of cooling. Results show that the higher the convection coefficient, the higher the power that the chip can consume for the same temperature. Also that the lower the coolant temperature, the higher the power the chip can consume. And that liquids are more effective for refrigeration than gases.
In this video, we have developed the first part of the 9th lesson. Watch the next video to complete this lesson.